Okay, so this is our first video on derivatives for Math 1560 Calc 1 at U of L for fall 2017. And in this video we're just going to look at the definition of the derivative and try to get some idea of where this definition comes from before we start trying to do things with it. Okay, so we start with the derivative at a point. So there are a few ways to kind of, we're thinking graphically, right? Historically, there's a few places where the derivative was motivated. One of them being thinking about velocity, but we can also think of things graphically. So the derivative at a point, the motivation comes from the following problem. You have a graph, something like this, let's say. We'll show you how to do this on the computer in a second. And there's a particular point on the graph. Let's say you're interested in, I don't know, this point right here. Okay. Okay. That's some point x equals a. And what you want is you want the what's called the tangent line when x equals a. So the word tangent here kind of comes from touch. You're looking for a line that just touches the graph. And so the idea is that you're looking for a line which passes through that point, and among all possible lines that pass through that point, it's going to be the only one that just touches at that point. It doesn't intersect anywhere else, right? So if you kind of adjust the slope one way or the other, you're going to find that you have a line that cuts the graph twice. But somewhere there's going to be this perfect line with just the right slope that it just hits that point. Okay? And that's the only place where it touches the graph. And one of the things, one of the reasons why this is useful, and you can kind of see from the picture, is that if we don't move too far away from that point, there's not a lot of daylight between that line and the graph. So if we stick around that point, that line gives us a really good approximation for the original graph, meaning that, the function that gives us this line, the linear function that gives us this line, gives us a reasonable approximation for whatever function produced this graph. And the reason that this can come in handy is that linear functions are easy, right? They're the easiest functions to deal with, other than, I guess, maybe constant functions, although really constants are a special case of linear functions anyway. So how do we figure out what this line is? Well, of course, we know a point on the line. What's the other ingredient that you need to define a line? You need a point, and so you need what? You need the slope. So how do you get the slope? Well, here's the problem. Here's where calculus comes in. Here's where limits are necessary, because we know how to get the slope if we have 2 points on the line. But we only have 1 point to work with. So what do? Well, we put a second point on our line. So we go over here and we say, let's just choose another nearby point. Okay? And we'll call that point x. So what is x? X is, it's a plus a little bit, right? Because we want to think of this h as a small number. It's telling me how far away x is from a. And then we draw the line that passes through those 2 points, like so, right? And so here's the kind of the slope that we want, right? We're looking for this, a line that looks something like that, y equals mx plus b. Really, we just need to know the slope because we already have a point, right? And so here we've got some other slope, and that slope, we can think of the slope for the other line as being a function of this h, right? Depending on how big h is, that slope is going to change. So let's consider this slope here. We'll call it maybe m. Yeah, let's call it mh. Okay, because it depends on this number h. So what is this mh? This slope. Well, we've got 2 points. We know how to calculate slope if we've got 2 points. It's rise over run, right? We calculate the change in x, and we calculate the change in y, right? And it's delta y over delta x. Delta y over delta x. Okay, but these 2 points are on the graph. They're on the graph of a function, y equals f of x. Okay, so I know that one of my points, I have x. Okay, and the other one I have a. So I know the change in x is just x minus a. The change in y, well, that's f of x minus f of a. Okay, and so that's the slope there. And so what are we trying to figure out? We're trying to figure out what happens as we shrink h, right? As we move those 2 points together, as we bring them closer and closer together, do we get what we want? And so, and there's a couple of ways we can do this as well. Notice that if we say x equals a plus h, we can also write this as f of a plus h minus f of a over, well, a plus h and then minus a. The a's cancel and just leave me with h. That probably looks familiar from some of the examples we did in class. When we talked about limits, we did a few different quotient examples, and we saw something like this, right? So let me show you how this works with the computer doing the drawing, so we can see what happens. So we can decide we want to move, let's say we move this point here and we move it along the graph, right? So we can see what happens. So notice as we move that point along the graph, the slope changes, right? And you can kind of see that, oh, there's going to be a point where they just come together. And so somewhere in there is the slope that we're looking for, right? Obviously here it's way off, here it's way off, but somewhere there, you're going to get that ideal slope. And the closer you come, the better your approximation is going to be. And you could also, there's a couple of different ways to look at it. You could also think about just kind of lines through that point, and you try different slopes, and you find the slope that seems to work best. There's a few different ways of thinking about it, right? But you do run into this problem that, you can't really calculate the slope when those 2 points collide. Because what happens when you calculate the slope when those 2 points collide? Well, you get 0 over 0. You get this 0 over 0 limit that you run into. But that's what limits are for. Limits are exactly for this problem of dealing with situations where you are trying to compute something like a quotient where it isn't quite defined, because you get something like 0 over 0, right? But you might still be able to get some information out. You might be able to get a limiting value. And this limiting value is called the derivative of the function at that point a. And the notation we use is this f prime of a. So this is the so-called derivative of f at a. Okay? So this is the graphical idea of where this is the motivation in terms of graphs as to where the limit comes from. Like I said, you can also think in terms of velocity, thinking about trying to calculate instantaneous velocity, right? Average velocity is easy. You take your distance traveled divided by the time, right? But if you shrink that time interval down to smaller and smaller and smaller intervals, you get closer and closer to your sort of instantaneous velocity, the thing that you would read off the speedometer, right, at any given time, right? If you take sufficiently small intervals, you get the derivative. Now, once you kind of learn how to kind of calculate the derivative at a point, so at x equals a, we have this definition: f prime of a equals the limit as h goes to 0, f of a plus h minus f of a over h. And we're gonna be doing a few more videos. We're gonna do a bunch of examples where we calculate derivatives directly from this definition. We're gonna be following up this video with a bunch of those. And one of the things that you're gonna see in those videos is that the role played by this a, you could replace a with any number and kind of do the same thing over again. And in fact, you could just leave a as a variable, and then you find that whatever value you want to plug in for a, you can plug it in on both sides and you get your answer. And so you can start thinking about what happens if I vary this point and turn a into a variable. And you can do this. And so what happens is, if you are given, so you're given a function f of x, and it's going to be defined on some open interval from say a to b, and you find that f prime of c exists at each point c between a and b. Well, once you have those, that means you can now get a new function by simply doing this derivative calculation at every point. F prime of x equals the limit as h goes to 0, f of x plus h minus f of x over h. And so this is sort of a derivative function in the sense that it's derived from the original function via this difference quotient construction. Okay, so we'll see lots of examples, and again we'll do a few where we calculate things directly from this definition, and then we're going to start developing properties of the derivative, and we'll find that we rarely need to return to this definition, at least not for the functions that we're familiar with. We'll end with one example. We'll do some more complicated ones next time. So let's say I want to determine the slope of the tangent line to this graph. So let me draw the picture for you. So we've got a parabola here, y equals x squared plus 1. We're at the point 1, 2. And we want to know the slope of this tangent line here. Okay, so what we can do is, now we're only interested in this particular point, right? And so what we do is we say, well, I know what the slope of this tangent line should be, right? The whole motivation we went through is that this derivative should give me this slope, and I'm interested in the slope when x equals 1. So I want f prime of 1 where f of x is x squared plus 1. So what's f prime of 1? Well, it's the limit as h goes to 0, f of 1 plus h minus f of 1 over h. So what do I get here? I get 1 plus h squared, plug that in for the x squared, plus 1, minus, so what's f of 1? 1 squared plus 1, 2, over h. Okay, so the limit as h goes to 0 of, well, what do I have? I've got 1 plus 2h plus h squared plus 1 minus 2 over h. I'm running short on space here, so let's do some kind of meta canceling. First, 1 plus 1 minus 2 gives me 0, so those all disappear, leaving me with this here. And notice here that I can divide both of these terms by h, so 2h over h leaves me with a 2, h over h, just h squared over h rather, leaves me with an h. And now if I let h go to 0, what do I get? Well, I've got the limit as h goes to 0 of 2 plus h. H is going to 0. I get 2 for my limit. And remember, that limit is my slope, so that means that my line is given by, so I do y minus the y coordinate, which was 2, equals the slope, 2, times x minus the x coordinate, which is 1. And I've got the equation of my tangent line. You could clean this up if you want, but let's leave it here for now.